All right, good. So now we can read the title. So this will indeed be about Higgsing 5D SCFTs from 3 different viewpoints, from geometry, branes, and quivers. And so all of these individually could be talked about at length. So this is not going to be super precise. I'm not going to explain everything in detail. And also, I'm just going to work with examples. And actually, I just kind of want to put together some different puzzle pieces, how they fit. And actually, the whole talk is here. This is all we'll do today. So I'll just briefly say what that is. Over here, we have a brane web, 5 brane web. Over here, we have the equations defining a Calabi-Yau threefold, a local Calabi-Yau threefold, something non-compact. And down here, we have something called a magnetic quiver. So this you can think of as a 3D n=4 gauge theory described with these nodes and edges. And we're going to look at Higgsing a five-dimensional conformal field theory. And we're going to see that this can be described in 3 ways. Once by pulling away a brane, sending it away. Once by deforming an equation with some term. And once by giving a VEF to a monopole in this magnetic quiver. And these 3 things, we'll see how they fit together. That's the idea. And okay. So before I really start, let me mention some collaborators. So many of the things that I'll say in general is either already known for a long time, or it's work done with Antoine Bourget, Ami Hanani, Markus Sperling, and Zheng Haozhong, and also many others. And then the stuff I'll talk about in particular today is done with Maria Marco, Michele Tezzotto, and Andrea San Giovanni. And all of these are here, so you can also complain to them. All right, so 5-dimensional n=1 SCFTs is what we're going to look at. And they can be constructed in 2 ways in string theory. And how this fits together is the topic of the talk at the example of Higgsing. So one way is to put M theory in some local Calabi-Yau 3. So we'll have an R1,4 left over. That's these are our 5 space-time dimensions. And the other way is to use a 5-brane web in type 2B string theory, ending the 5 branes and 7 branes. And the 5D field theory will be on the world volume of this, which is actually 5-dimensional due to the 7 branes being present. So in this geometric engineering picture, the Coulomb branch of our theory is described by the resolutions of our Calabi-Yau threefold. And the Higgs branch is described by complex structure deformations of this threefold. And in the 5-brane web, the Coulomb branch is described by some breathing. Down here, there's a 5-brane web, and it's breathing, by some breathing modes of the web. And the Higgs branch is described by decomposition of the web. We'll see an example later. And if we're dealing with a toric Calabi-Yau threefold, then there's a very nice duality to a very specific brane web. So there are also so-called toric brane webs, and then there are others. And yeah, if everything is toric, then it's super nice to match these 2 approaches. And this is also the round that we will be in, but then leave by Higgsing. Okay, so the Coulomb branch of a 5D SCFT is very easy to describe both in the geometric engineering and in the brane web construction. So we're not going to talk about this. This has been done 20 years ago, and it's really nicely understood, and it's just not a problem. The Higgs branch of a 5D SCFT is not, or we could say is barely understood in the geometric engineering approach. So the Higgs branch people typically think is kind of the easier object because we learned it's classical or something, but this is just not true. This is only the case if you're dealing with a Lagrangian theory. A 5D SCFT is not Lagrangian. It could maybe have a description as an effective field theory if we deform it, but it is not itself Lagrangian. So the Higgs branch is actually a super hard object because we can't use any of our field theory methods to compute it. But it is, by now, really well understood if we have a brane web. This goes via something called magnetic quivers, which I will briefly introduce, but yeah, I will not say so much about them. So the goal is better understanding the Higgs branch from this so better understanding the Higgs branch in the geometric engineering picture using the intuition that we get from brane webs and these magnetic quivers. Okay, very briefly a brane web. We have type 2B string theory. Given the name of the conference, we know what that is, and we know that there is branes. I'll just say how they are fitted inside our spacetime. So we have the 5 branes, which span the 0 to 4 and the 6 direction. NS5 branes, which span the 0 to 5 directions. And then we have PQ5 branes, which you get by merging a D5 and NS5 branes. So PD5 branes, Q, NS5 branes. And they are at some angle. And there will also be PQ7 branes, which is where the 5 branes end. A PQ7 brane is kind of just like your standard D7 brane, but the monodromy is a little bit funky. But we don't have to get into the details here. So let's see how we actually construct a theory here. Well, if we take some parallel D5 branes, we would get some 6-dimensional super Young-Mills theory. Terminating this on NS5 branes actually gives us some 5-dimensional field theory. And there is, of course, the bending of the branes due to the charge. So here we constructed some SUN level 0 pure gauge theory. We can turn on the level by bending the branes a little bit, and we can also add flavor. This is all pretty straightforward. Now we know how to construct any SQCD in 5 dimensions. All right, so that's a brane system. Now, what are the moduli? In supersymmetric field theories, we always have some, or not always, but we usually have some interesting modular space of vacua, which is kind of the most basic object to study when studying any of these theories. Of course, first we want to know about the vacua. So here I took as an example SU2 with 4 flavors, 4 fundamentals, and this is at finite coupling. And the brane web corresponding to this looks like that. And there is the Coulomb branch, which of course we won't discuss as I already said, but I still want to show it. The Coulomb branch is achieved by separating the D5 branes, but kind of along the NS5 branes. This will leave an abelian vector multiplet and otherwise Higgs the theory along the Coulomb branch. The other option is going to the Higgs branch. And here now I'm doing some modern art. I'm actually trying to draw the 3-dimensional setup, or approximating this by a 3-dimensional setup. So these are 7 branes here, and the 5 branes are being moved along these 7 branes. So I can count the number of moduli that I have. On the Coulomb branch, there's just one phase I can open up, 1-dimensional Coulomb branch, which fits the rank of our theory, that's good. The Higgs branch, here we see that we have 5 independent brane segments we can move. There is an overall center of mass we get rid of. And if you do the classical computation, this is exactly the dimension of the Higgs branch. So the branes, they see your moduli space. Now, the geometry of the moduli space is, especially here of the Higgs branch, is not yet captured. We have the dimension. It's already a start. So we will now suppress these x 7, 8, 9 directions because drawing the 3-dimensional thing is just outrageous, and we can just use colors instead to denote another dimension. So I've colored the branes over here. This stands for moving them along the 7 branes. And now if I want to know the geometry of this Higgs branch, I can extract something called a magnetic quiver, which was introduced by Cabrera, Hanani, and Yagi in the 5D world. And there have been many, many works on this. So I'm not going to say how, but very roughly all the branes, they become a node, the different kind of brane segments, and then the edges are gotten by using some tropical geometry from these brane segments. And now, okay, we have some quiver. So the key equation is that the Higgs branch of our theory, and that here, this is just some classical Higgs branch because we're at finite coupling, is going to be the 3D Coulomb branch of this magnetic quiver. And this is reminiscent of 3D mirror symmetry. And nevertheless, this is a statement that we're making in 5D. We're comparing a 5D theory to some 3D theory. There is no 3D mirror symmetry, but the Higgs branch of one is the Coulomb branch of the other. So this is, let's say, a computational tool. One can say more, but let's just view it as that. And this is a classical computation. We can see that this is true. And now what about the SCFT fixed point? Well, we can look at the brane web corresponding to SCFT fixed point. And we can, in just using exactly the same rules, extract a magnetic quiver for this as well. Now, this is actually quite neat that the complexity or the difficulty of the computation stays the same, whether we're dealing with some super vanilla Lagrangian theory where everything is classical, or this super hard to describe 5D SCFT, which we have barely any control over. So that's actually a fantastic object because it doesn't care whether it should be easy or it should be very hard. The computation is always easy. So that's why we like magnetic quivers. And in this case, we can also see that the infinite coupling theory has now 7 moduli, Higgs moduli, and we can do the computation. We can check what this magnetic quivers gives, and it actually fits the known answer. Okay, I don't want to go too much into the details. I want to now actually address Higgsings. So now, what is a Higgsing? Well, Higgsing is moving along the Higgs branch. It's just a different name for that. So in other words, in field theory, we're giving a VEV to some field, and then we'll see what remains. So I'm not caring about any massive stuff. I just want to see what's the effective field theory at low energies. And of course, we don't have any direct field theory description for our 5D SCFTs. But in our brain picture, we can take our brain web, and we can just take one of these segments, send it away, and we just see what remains. That's a Higgsing in a brain picture. And we're left with this down here, which describes free hypers. This is obvious if you know about brainwebs, and if you don't, that's fine, just believe me. Now, on the magnetic quiver side, we can give a VEV to a monopole operator. That would be now moving along the Coulomb branch of this magnetic quiver, which is the same as the Higgs branch of our 5D theory. So here I could take, for example, this node over here, and I just give a non-trivial VEV to the monopole operator, the basic monopole operator associated to that U1. And if I do that, then what remains is this theory down here. And this is a theory of free twisted hypers, so abelian vector multiplets in 3D. And so this perfectly fits. So brainweb, magnetic quiver, they're kind of the same thing. They see the same stuff. Now, I want to go to the geometry. And in geometric engineering, the same theory is described by this equation, this set of equations here, which comes from this toric diagram, which is just dual to the brainweb that we just looked at. And so this is some local Calabi-Yau3 singularity. It's a complete intersection. There are two equations, x, y is z squared, u, v is z squared. So these are kind of intersecting Kleinian singularities. And now, as I already briefly mentioned at the start, the Higgs branch is captured in geometric engineering by looking at deformations of the singularity, so opposed to resolutions which capture the Coulomb branch. Now, we can actually write down a complete set of deformations of the singularity using results from Colinucci and Vallandro. And this is what we have down here. So I'll put some parameters, alpha I, and then some monomials which capture the deformation. And if I turn all of these alphas to some generic value, I have a completely smooth Calabi-Yau3 fold now. And then we're on some generic point of the Higgs branch where we're just left with some, yeah, basically nothing anymore. Okay, so now we can turn on just some single deformation. And I picked that xy equals to z squared stays the way it is, and uv equals to z squared gets an additional alpha 1 x. Well, this alpha 1 is not 0. So the singularity that remains, if we analyze the singular part, is actually a so-called compound Duval singularity. And these compound Duval singularities engineer free hypermultiplets. This we can get from a paper of Colinucci, Marcos, and Giovanni and Vallandro. And so, again, this fits with the side of the brainwebs and the magnetic quivers. We're left with free hypers. Everything is consistent. That's nice, is what we expect. Okay, and now we can actually take this deformation and we can map it exactly to the brain that we just moved. Why I can do this is definitely not clear from what I've said so far, but I can say this with quite some confidence. And so this alpha 1x is basically corresponds to moving this brain segment, or in other words, this alpha 1 I could interpret as the vacuum expectation value of my monopole operator in this 3D magnetic quiver. These things are all kind of the same. Now, we can also add the other deformations, everything that corresponds to moving some single brain segment. And so we have alpha 1x and alpha 2y deformation. I should have really put the equation here again because this is not very clear. Let me briefly jump back to the equations. So we have two equations. And the one set of equations we can deform by x, y, and z. The other set of equations we can deform by u, v, and z. And over here, the x, the y, and the z are the D5 brain moves, and the NS5 moves are given by u, v, and z for the other equation. So we kind of have some mapping between these deformations, between moving brane segments, and between these monopole webs. So let's take something a little more interesting. SU3 with 6 flavors at its infinite coupling UV fixed point. I'm putting a little hat here to say that it's at infinite coupling because I don't know how to do it better. And the brane web is over here. This is the magnetic quiver. Everything looks kind of similar, just a little bit longer. That's because it went from SU2 to SU3. It's not remarkable. These things should look similar. And down here, the equation is changed only in a tiny detail. This is Z3 instead of a Z2. Now, we can look at the deformations here, and of course, it's getting a little out of hand because the dimension of the Higgs branch is just growing. And actually, we count 12 deformations, which fits the Higgs branch dimension at infinite coupling. And so what can we do with this whole mess? We don't see any structure here straight away. We would have to do some difficult computations to see what is the kind of theory, what is the kind of singularity that remains if I turn some of this on. But now I'll just kind of state how these things fit together, because I have all this technology from brane webs and magnetic quivers. So we can look at the partial Higgsings of our theory. And partial Higgsings can be captured in what is called a Hasse diagram. Hasse diagram is just partial order as a picture. That's it. So, and nothing fancy. So partial Higgsings, of course, are partially ordered, and that's what I'll show you. So over here, we have the theory SU3 with 6 flavors at infinite coupling. And it can be Higgsed to either SU2 with 4 flavors at infinite coupling, or it can be Higgsed to SU2 with 5 flavors at infinite coupling, or inequivalently to another SU2 with 5 flavors at infinite coupling. And these all can be further Higgsed, and then we reach a trivial theory, which means just 3 hypers. And over here, we see the corresponding magnetic quivers. So down here, we have the full magnetic quiver. These are the moduli that are still at our expense. We can do some Higgsing. We have less moduli left. And what are the moduli that we should have left? Well, exactly, we should find a magnetic quiver of the theory that we just discussed. And indeed, this is what happens. And over here, we find 2 magnetic quivers. And this set of magnetic quivers are exactly those that fit inside our original magnetic quiver and that don't contain any free stuff. So we kind of know all of the theories that we can Higgs to. And now we can group our deformations of before into these different nodes in our Hasse diagram. This is all the same diagram. And we see that the deformations like x squared, xz, z squared, yz, and y squared, which kind of corresponds to d5s, they all belong to the same Higgsing, which is also seen down here. This, to get from down here up to here, we have to subtract the -1 from all of these 5 nodes. And actually, if I subtract the -1 from one of them by turning on some monopole VEF, what I'm left with is something that includes some free twisted hypers. I can take them away, and then I'm left with exactly this. So any one of these deformations will do to Higgs me there. And in order to completely Higgs, I can do 2 things. I can turn on a deformation that is not named here, or I can pick one of here and one of here, and this will also bring me there, because, yeah, kind of clearly. So now we've brought in some logic into these deformations. Okay, so the nodes in the Hasse diagram, they correspond to symplectic leaves in the Higgs branch. Now, if you don't know this language, that's fine, but the Higgs branch is some hyperkähler variety, and it's stratified by using the symplectic form. And the stratification matches exactly the partial Higgsing of the quantum field theory. This is quite remarkable, but also if you think about what a moduli space is, it's kind of obvious. So this is just a fact. And now we can fit these deformations into the same Hasse diagram. So we can see that using the deformations, we can probe the singularity structure of the Higgs branch. This is not the same as knowing what the Higgs branch is. We don't know how to obtain the geometry of the Higgs branch from these deformations. That's actually still a very hard problem. But we now have some path towards it. This is kind of, the goal would be to get the Higgs branch just from our deformations. But well, we don't get quite there, but we at least understand the singular structure. And so the things we did, they match were applicable with the work of Bourget, Kulinucci, and Stefanameki, and also Alexeyev, Argus, and Bousseau, just for those that know these things. And yes, I'll get to my outlook. I think it's time. So how do we obtain the full Higgs band from geometry? Still an open question, but hopefully we can make progress. And a thing that I haven't mentioned at all, but I've mentioned at the beginning that if we are dealing with toric brainwebs and toric geometry, there's a very nice duality. So there's a kind of a one-to-one correspondence between these. And this is lost once we lose toricity. But actually, moving these brain segments and turning on these deformations and being able to match these two, we now can also match non-toric geometries and non-toric brainwebs to some extent. So this is something we want to also explore in the future of how to deal with what is also sometimes called white dot geometries, which go beyond the regular toric diagram geometries. Okay, with that I'm done. Thank you.
Thank you. Thank you. Questions for Julius?
Hi. I had a question when you match deformations to brainweb things. The constant deformation didn't show up. What does that do?
The constant deformation?
Exactly.
Yeah, that's kind of you send everything away. Like you completely kill the singularity. Yeah. So the things that I've showed you so far is to pick a single brain and send it away. I've kind of swept under the carpet that there are other deformations which are more violent and they just send more away. And the constant one sends everything somewhere.
No, thank you.
Further questions, comments? Well, thank you again.
Thanks.